Our idea of visualizing an area as a sum of a bunch of sliced up little strips, whether those strips are oriented vertically or horizontally, allows us to build an area finitely. I want to do the same thing with a volume. We start with a simple shape, a cylinder. Now, when I say cylinder, most of you think of a shape like this. This is what is referred to as a right cylinder. The reason it's called a right cylinder is because the base and the height make a right angle with each other. But this is even more. This has a base that's a circle. But you could describe a cylinder, a right cylinder, over any shape. Right? Here's a parabola for a bottom. I cut out a piece of a parabola, and I go straight up. What is the volume of the right cylinder whose base is a circle?
Maybe pi r squared times the height.
This idea of looking at the same shape all the way up even extends to a box. Think about our rectangular box. I've got a length, I've got a width, I've got a height. The volume of the box is the product of those three, yes? But let's group. The length times the width is the area of the square or rectangle that is the bottom of that box. Here, in our circular cylinder, the pi r squared is the area of the circle at the bottom. If I knew the area of this parabola, then the volume here would be that base area times the height. So in general, the volume of a right cylinder is base area times height. My water bottle is not truly a cylinder. Narrower at the top than it is at the bottom. Now, this is not a new water bottle, it's an old water bottle. Eventually, the markings on the side are going to wear off. What's the volume of this bottle? I can tell you how much water it's supposed to hold, but what if I actually wanted to know the volume, even including the plastic itself, the actual size of space that this bottle, even including the lid, takes up? Well, then at different heights, it's got a different area. Let's chop it up. On page 438, page 439, we see a shape. It's a very strange looking shape. And as we go from left to right, it is clear that this shape has different areas at different places. So I could imagine taking a slice. Oh, look, it's a loaf of bread. We'll slice up the bread. Look, calculus is the greatest thing since sliced bread. All right. What if I imagined slicing this and then thought of every slice as a cylinder. Well, that wouldn't be exact, but I could approximate my shape with a bunch of slices. And then each slice would have some area and some height. Only in this case, the height is sideways. It's all right. That means my height is a change in x. Oh, I like this, because then I could think of my volume as the sum of a bunch of slices. Wasn't that exactly what we were doing for our areas? So if I can write the area here in terms of x, then at each x value, I have a function of x. Area times thickness is the volume of that slice. How many of you have seen a 3D printer in action? Okay, a 3D printer takes a solid object and builds it a slice at a time. The amount of plastic we lay down in each circuit of the shape is the volume of one slice. And depending on the 3D printer, you can have a very thin slice, a very thick slice. And thus you can make different visualizations of our chopped up object. And then our volume becomes a sum. Now notice I wrote A of xi star. Well, that's because I don't know what x value I'm going to use in each little slice to decide on the slice's area. I could use the left slice. I could use the right slice. I could use an x value in the middle. But that's an approximation. Let's take the limit. As our slices get smaller and the number of them goes to infinity, what happens to this sum? Sum becomes an integral. Where here A and B are the left and right edges of our shape along the x-axis. As long as I can find a function to slice stuff up, this works perfectly. Now, the question becomes, what's the right slice? And it really depends on the way we are building our object. Page 444, example 7. I'm jumping around in the text a little. Here's a shape. The shape is built by taking a circle. And at every slice along the circle, we put an equilateral triangle whose base is along the circle. So there are small triangles at this end, big triangles in the middle, and small triangles at this end, and our thing looks like this. You can actually see the triangles in the grid lines here. Oh, I need a function for the area of the triangle at point X. But an equilateral triangle will be here. And that means its base is twice the y value along the circle. Wait a minute. I know the equation for this circle. The equation for the circle that. So the base of my circle, the base of my triangle is twice that. And now I need a little trig. I need to find the height. Wait a second. This is an equilateral triangle. The angle in any corner. So that's add up to 180, and they all have to be the same because all the sides are the same. What is the sine of 60 degrees? Now you know why I keep making you take trig before we take this course.
Root 3 over 2.
It would be root 3 over 2. But trig applies to right triangles, yes? So this is the y value. Tangent, opposite over adjacent. Tangent is square root 3. So I take this side and multiply it by square root 3. Or I take the y, which is this side, plus unknown equals, I don't know the length of this side, do I? See the problem? So it's easier to do it this way. And then the height is square root of 3 times the square root of 1 minus x squared. Now I know the formula for the area of the triangle. Area of the triangle is 1/2 base times height. And fortunately for me, lovely simplification occurs, and I end up with a very nice area formula. The 1/2 and the 2 cancel. I have 2 square roots of the same thing, so I can combine them. The circle has radius 1. So my shape goes from -1 on the left to +1 on the right, and that means the volume is the integral from -1 to 1, area times thickness. And fortunately for me, that is an easy integral to compute. We got the 1 and the -1 from the fact that the circle itself is of radius 1. And thus, the smallest x all the way on the left for my area is -1, and the biggest one is +1. In this particular example, I had to work out the slice function. What is our function a of x that measures a slice at any given height? Yes? But if I was working with my water bottle, something very nice about that bottle, something very nice about decorations like this one that I got at the party store. This describes a curve, yes? This lovely shape here. And I can think of this shape as being rotated. Let's create something called a volume of rotation. Take a given object, a given curve, and spin it. When you take a straight line and you spin it, you're making a cylinder, aren't you? Okay, if you tip the line and hold one end still and spin the other one, you're making a cone. So volumes of rotation or volumes of revolution come from taking some curve and spinning it. I want to do that. I want to take a curve, f of x, and I want to rotate this around the x-axis. Now, I can actually physically do that with this object. Best part about that, party supply store already did it for me. Notice that the side of this object is exactly the curve I was just talking about, yes? There's my curve. I spin it around this axis. Now I'm going to slice this sucker up. When I do that, I'm slicing it what shape do I get? A circle. As a matter of fact, in any solid of revolution, my cross section should look like a circle. Well, if my slice is a circle, then I'm going to have a huge advantage. The advantage is, what's the area of a circle?
Sorry, that's square root of r squared times
Pi r squared, right? So let's think about this circle, the one we just pulled out right here. So I have this circle standing on edge, I pull it out, I lay it down, and I start looking at it. What's the radius of this circle? Well, where is that radius in this picture? That would be unrelated to the circle I've drawn. I mean, the circle is at some particular x value along there, right? Let's give that a name. Let's call this spot x0. That's where I took my slice. Here's my slice. Right here in my hot little hand. What's its radius? On here, picked this thing up and I set it down. That means the axis, the x-axis, is pointing straight out at me. That dot in the middle is all I see because I'm looking down this way. Here's the radius. Of that slice. Where is that stick? Over here. Corresponding y value. This stick goes from our center point up to where we hit the curve, which makes the radius, the y value, given by our function. Which means I now have an area for this slice. Because Gavin, you told me the area is pi r squared, but r can be written in terms of my x. Which means the volume is the sum of all my little areas. It's the sum of my slices. And this time, Jack, this time I hope it's much clearer where the A and the B come from, right? That's where we're starting and ending our cuts. So in this case, that's going to be pi f of x squared dx. Which means if I am doing a volume of revolution, a volume of rotation, I know exactly the formula for the area involved. Okay. Let's find the volume that results from rotating the curve y equals square root of x, from x equals 0 to x equals 1, around the x-axis. I should write a complete question. Find the volume that results from rotating y equals root x from x equals 0 to x equals 1 around the x-axis. So now, what's my shape look like? Graph of the square root of x looks like this. And I'm going to spin that, which means you can picture it on the screen in front of you coming out towards you. It'll eventually rotate all the way around. It'll hit the screen again. Then it'll go up behind the screen and we'll have a sideways oriented bowl. Matter of fact, I'm going to draw down here the mirror image half We go around, and then we come back up like that. I freely admit to being a crap artist, but at this point, bad art is still helpful. A bad picture is still useful. If you would like a better picture, take a look at page 441, figure 6. Theirs is much prettier than mine. But you see how we have a slice? And when we spin that slice around, we get a coin. So if I were to lay that coin on its side, I'd have a circle. There's my slice. And at that x value, I have a circle whose radius is the function I was given, the square root of x. Which means I can find the volume of this particular solid of revolution. The only other thing I need are the limits of integration on that particular integral, but they were given to me in the problem explicitly. Ta-da! When you square a square root, what happens? So I'm just integrating x. I'll pull the pi out front, leave it there because it's a constant. Then I get x squared over 2 from 0 to 1. Well, that's 1/2 minus 0/2, which is just 1/2. Questions?
Is the radius usually just like the function?
That's really the question. In this case, I think of the radius as the distance from the curve to the line I am rotating. Yes? And in this case, it said I'm rotating around the axis, so that statement is correct. But what if I pick a different line? Let's take this same idea and change it just a little. Now, I actually end up with two problems when I do this. I'm going to draw the same picture. But I'm now rotating around this. Uh-oh. My region doesn't touch the line I'm rotating around, does it? I'm sorry?
We can still rotate.
Sure. But what I'm going to get is I'm going to get this shark fin way down bottom, right? This is a unit away. So the bottom of the fin is going to be here. Oh, crap. I do just get bigger circles, but I have a different problem as well. What do you see here in the middle?
That's a rectangle.
That's a hole. My object that I have created is hollow. It's not solid anymore. What I have is a ring. Which means my cross section isn't a circle. It's actually two circles. Let's again pick an x value. Draw that little stick. Now, we spin that stick, which means this dot ends up here. And this dot up at the top ends up here. My stick is not described a circle. My slice is hollow. It's a washer. It's one circle inside another. If I want to be a mathematical geek, the math name for this is an annulus. I could. The textbook calls it a washer. I'm good with that. What's the area of the washer itself? I don't want the area of the hole in the middle. I only want the area of the physical washer itself.
So we take the area of the entire thing and then subtract the area of that one circle.
Which means I need two circles, the outside circle and the inside circle. The area is a difference of two circles. And I'll use R out and R in for the outer radius and the inner radius. Some books use a capital R and a lowercase r. I'm good with just using the subscript to tell me which one I'm looking at. Now, let me answer the question you came up with. What's the radius? Let's look at the point that is the outside edge. That would be this point up here, yes? And that would mean that the outside radius goes from here to the line we rotate around. How do I find the distance between 2 points?
So it's two different y. So all you gotta do is subtract your y.
The y of the top minus the y of the bottom. But the y of the top, that's our curve, yes? The y of the bottom is -1. What's the inner radius? Well, that goes from here to our rotation line, yes? So R in is right here. What's that distance? That's y equals 0, and I'm subtracting -1. That's 1 all the time. So now I get a slightly more complicated problem because the area of my slice is different. So I need to take into account two different things. And these are both important, Dominic. I need to take into account where am I rotating? Is the object touching the line of rotation or not? Because that's going to tell me whether I have a solid disk or a washer. But notice the formulas are still circles, pi r squared or pi r squared minus pi r squared. The best part about this is we can still do this calculation. This integral is not all that much harder as long as I do the algebra correctly. Because what I have to do is I have to square this out. And this one's easy, but this one, I have to remember to FOIL it out. So I get x plus 2 root x plus 1 minus 1. I'm going to factor the pi out of this whole thing. And these two cancel. And that means that my volume is still an integral from 0 to 1, but it's of a different function. So a volume of revolution, volume of rotation, comes in two flavors: disks and washers, depending on where the rotation axis is. Square root of x is x to the 1/2. So I'm going to get x to the 3/2 over 3/2. Since I am multiplying by a 2, I'll pull that fraction out, flip it over. And I get a 4/3. Plug in 1, plug in 0. One half plus 4/3. Let's do it in sixths, right? 3/6 and 8/6 is 11/6. So there are two different important pieces here. Piece one is to figure out what your radius is. And piece two is to figure out whether you've got a disk or a washer, to know whether or not you need one radius or two radii. This is why I draw crappy pictures, because crappy pictures help. More questions? I believe the textbook uses the example where we have y equals x and y equals root x. And we're rotating around the x-axis. So my question to you, is this a disk or a washer? That way I know how many radii I need, and then I can figure out what they are. Let's draw a picture. What's this shape look like? I saw this shape yesterday. I'm sorry, Monday. It's been a while. The straight line, y equals x, and the parabola, y equals x squared, but they meet at 0, 0, and 1, 1. Which means when I spin this, I get something that has a hollow inside it, right? Think of a slice at some x value, and we spin it around. Again, crappy pictures help. That's a washer. It's got an outside ring and an inside ring. Page 442, here's the little slice they took. Here's what happens when I spin it, my inner radius and my outer radius. Wait a minute, inner radius, outer radius. Dominic, what's my outer radius in this case? You tell me.
I knew the y equals x
Would be?
part of it.
Yes, it's the top part.
Yeah.
Where are we rotating around? We're rotating around the x-axis. And the y value for the x-axis is?
0.
So the outer radius is just x. What's the inner radius? Ta-da! Please notice, if I change the line I am rotating around, I will change these. And as a matter of fact, again on page 442, they do exactly that. Same shape. But this time, instead of going around the x-axis, go around the line y equals 2. That's up here. So here's the same shape, but it's being spun a different way. And not only does it change what the radius is, it changes which one is inside and which one is outside. Because notice, this time, what's closer to the line we're working with is the top of our shape. So the inside radius goes from 2 to the line. And the outside radius goes from 2 to the curve. So I have R in and R out. They switched. I need to know where I'm looking for my inner and outer. I need to know where I'm rotating around. I honestly believe I could not do this problem without the picture. I'm sure if I thought about the algebra long enough, but the picture is just so helpful to me in intuiting which is inside and which is outside. What are the actual radii? Better? Wonderful. So let me use some more. I'm going to take the same shape and I'm going to rotate it differently. I'm going to turn this rotation. Remember, I have a parabola and I have a line, but now instead of going top to bottom, I'm rotating left and right. I need to redraw my picture. The other piece now is not down, it's across. What happens is that my circles are not oriented the same way. Where's my circle? My circle is now this way, which means its thickness isn't X, which means my sides need to be in terms of Y, not in terms of X. I'm not slicing up and down, I'm slicing across, just like we did on Monday. I changed the orientation of my picture. Well, that means I need to change the way I write the equations. The inside equation and the outside equation now need to be written in terms of Y. So the outside equation, y equals x squared, becomes x equals root y. And the inside equation becomes x equals y. And my thickness is dy, not dx, which means I'm going to do this integral like it was a stack vertically, like I would do the water bottle sitting in front of me, like my 3D printer does. It goes from bottom to top, not side to side. So this becomes same sort of integral, just sliced the other way. Now I did this around the axis, so this is really x minus 0. Yes? And this is x minus 0. But I could rotate around a different line. Rotating around the line x equals minus 1 makes this a much bigger thing, doesn't it? But that changes the inner radius and the outer radius. It's square root of y minus negative 1. That's square root of y plus 1. It's y minus negative 1. That becomes y plus 1. It's always side minus side, like it was top minus bottom. I just have to go from right to left instead of from top to bottom. Volumes of rotation and volumes in general allow me to drive my slicing behavior differently. Tomorrow's question. Draw me a picture of what's going on with this equation around the y-axis. Tell me why what we've done today doesn't work. Tomorrow, I need a different method. Try and do this picture. But that's tomorrow. So I will see you all then. I hope you have a wonderful day. If you came in late, please come get your homework. That's how I took attendance today. Say again?
Q&A's on.
I believe so.